Good evening, one and all. So today we are going to see actually last combination logic circuit actually, which is encoder. Okay. So in the earlier class, previous class, we have seen about the decoder, which is actually also called the min-term generator. Okay, and we have seen how to design a decoder. Okay, and also we have seen a basic decoder. It's a 2x4 decoder, and with the help of 2x4 decoder, we have also implemented half adder and half subtractor. And we have seen that to implement the half adder and the half subtractor, we need one 2x4 decoder and one OR gate, okay, for both the cases. And also we have seen another type of decoder, which is actually 3x8, and we also told that it's binary to octal decoder. And after that we have seen how to implement higher order decoders using lower order decoders. Okay, and in this class we are going to start with the encoder. Encoder is nothing else, it's again a combinational logic circuit. Okay, combinational logic circuit which has many input and many output. Again the same thing, which have many input and many output. Okay, many input and many output. Okay, now encoder is used to convert, mainly what is encoder? Encoder is used to convert other code to binary. Okay, other code to binary, other code to binary. So in decoder, what we have done, students, a decoder mainly converts the binary code to other code. Okay, we are converting binary to binary to octal, we are converting binary to hexadecimal, bc to decimal, bc to 7 segment and all. Okay, but here in this encoder we are able to convert a different code, means an octal code to binary. Let's say examples are here. Octal to binary. Okay, next decimal to bcd, like this. Again I have told you what is bcd. Bcd also a type of binary code. Okay, and hexadecimal to binary. Okay, hexadecimal to binary. Okay, so mainly what is encoder now? Encoder is a combination logic circuit which has many input and many output, and which converts other code to the binary code. Okay, so my like examples are octal to binary, decimal to bcd, and hexadecimal to binary, like this. Okay, so these are actually basic basic encoder circuit. So we'll see what is actually the basic encoder circuit. You can see one of the encoder circuit, which is actually first of all I will tell you how the encoder symbol will be. The encoder symbol will be, it has many input, obviously it has many input. Okay, and it has many outputs. Okay, so mainly encoder is actually a 2 to the power input to n input, n output. Okay, it converts actually 2 to the power input to the n number of output. Okay, so it's actually called 2 to the power n to n encoder. Okay, so this is the basic symbol, nothing else. Now you see here what it actually do. Let's say I will be having one basic encoder circuit, which is nothing else like octal to binary encoder. So octal to binary encoder means what? Octal to binary, as I told you, encoder will convert any number, any code to a binary code. So octal is any code which actually converts to the binary code. So obviously octal means what? It has 8 inputs. Okay, so 8 inputs means 2 to the power 3 inputs. Okay, and how many outputs you can expect? 3 number of outputs. So octal to binary means it actually converts 8 cross 3 encoder. It's actually 8 cross 3 encoder. Okay, so very simple. Do you all understand about it? Some issue is there. Okay, so here basic encoder circuit which has many input and many output. So 2 to the power n input to the n number of output. So we have seen that it's a 2 to the n into n encoder. Okay, so we have discussed about it, octal to binary encoder. In case of that octal to binary encoder, what it will do? It has 8 number of inputs. 8 inputs means 2 to the 3 number of input, and it converts to n number of output. N number of output means 3 output. So obviously 2 to the power n is 3. So here 3 output. So it's actually, if it is an octal to binary encoder, it's actually nothing else my 8 cross 3 encoder. Okay. So we'll see how the encoder works actually, nothing else. Encoder mainly what it will do, it converts any other code to the any other code to the binary code. Okay, so we'll see one basic octal to binary encoder. So octal to binary encoder. Okay, so as we know that it's a combination logic circuit, what you need to do, we need to find out how many number of inputs and outputs required for it. The mainly it require actually 8 number of inputs. So 8 inputs are, let's say, I0, I1, I2, I3, I4, I5, I6, I7. So these are I0, I1, I2, I3, I4, I5, I6 and I7. These are my 8 inputs, and this is my 8 cross 3, which is octal to binary encoder. Okay, and it has 3 outputs, y0, y1, y2, y0, y1, y2. Okay, so these are the 3 outputs. So mainly what it will do in normal encoder, one of the input line is high and corresponding binary output will be available at the output. So what it will do in the normal encoder, any of these input will be high. Okay, let's say this input is high, so I3 means obviously what I will get here, I will get output like 0, 1, 1. Okay, so if any of these at that time, I will be having other inputs are 0. Do you all understand now? In normal encoder, what it will do, one of the input line is high, and corresponding binary available at the output. Okay, so you see here, if I5 is 1, obviously other bits are 0. Okay, as we told that one of the input line is high, one of the input line means I5 is 1, other bits are all 0. So what we will expect here, I5 means 1, 0, 1 will come. So like this way it converts the octal numbers into the binary numbers. So see here how it will do actually, how the truth table will work. So mainly the truth table will be here. Very simple. It has 8 inputs like I7, I6, I5, I4, I3, I2, I1 and I0. And what is my output I can expect here? Output will be a 3-bit binary, which is Y2, Y1 and Y0. Okay, so see here, first let's say I0 is 1. So obviously what I will get at the output, I will get 0, 0, 0 as binary code. Okay, next I1 is the input line high, so at that time I will expect output will be 0, 0, 1, and other bits are 0, students, don't worry. So these are all 0. One of the input line is high, other input lines are 0, low. So then I will expect like this type of codings. Next, say I2 is high, other bits are obviously 0. Okay, I'll just, I'm not putting next time or not. So here I'll get 0, 1, 0. So these are the binary codes. Let's say I3 is high, so what I'll get, 0, 1, 1 at the outputs. Next, I4 is high, what I'll get here, 1, 0, 0 at the output. Next, I5 is high, so what I'll get here, 1, 0, 1 at the output. Next, I6 high, so it will be 1, 1, 0 at the output. Okay, last at the end, I7 is high, I'll get what actually at the output, 1, 1, 1 at the output. So this is my corresponding truth table of the 8x3 decoder. So you can see how is actually converting. Obviously you can see that it's actually what actually nothing else. My you can see these are my 8 inputs. From those 8 inputs, which is actually the octal. How is it octal, student? You can see I0 is 1. I0 means 1. What is the value of it? 2 to the power 0. 2 to the power 0 means obviously it's a 0. I0 is 0 means it's 0, 0, 0. At 1 it's what actually 1 it will be I1. I1 means it's 1. 1 means 0, 0, 1. I2 means at I2 2 means it's 0, 1, 0. I3 means 3 means 0, 1, 1. 4 means 1, 0, 0. So all of you know that what is octal. Octal is nothing else starting from 0. So 0, 1, 2, 3, 4, 5, 6, 7. So this is only octal. 0 will be represented at I0 is 0. Okay, means it's logic 1 at I0. Okay, these are the corresponding octal values, students. So the suffixes, so these are I6, I7, 0, 1, 2. So what it will do, it converts those octal numbers into the binary equivalent like this. So this is the circuit which converts my 8 inputs, okay, into 3 output lines. Okay, that's why it's called the encoder, and it's nothing else my octal to binary encoder. Okay, any doubt on this? Next, how will be the logic expression now? how to find out the logic expression, what I told, how to find out the logic expression. The third bit is logic expression, how to do it, logic expression. So see here, my outputs are what actually? Y0, Y1 and Y2. These are the three outputs of mine. Okay, how to get Y0 actually? How to get Y0 actually? Y0 will be nothing else, my 1 will be here. 1 will be here means what? At that time, what is the corresponding one here? I1. So I1 plus what is there here? This one I3. I3. Okay, next similarly here 1. So I5. Next I7. Okay, so this is my output. Next Y1 will be similarly, Y1 will be nothing else. Y1 will be what? Y1 actually this is 1. This one means mine I2. Okay, like this way you can do I2, next I3, next I6 and I7. Okay, next what is Y2? Y2 means this is 1. So this is 1 means I4. Okay, I4 at that time this I4, next I5, I6 and I7. Okay, so these are my logical expressions. Okay, do you all understand now? This is very simple. So this is basic encoder circuit. Now how to design this? We know that it's very simple. We have actually how many inputs are there? There is actually 7 inputs. So my encoder circuit must have 7 inputs. So see here it has mainly 7 input, 8 inputs, as octal number consisting of 0 to 7. So it has 8 inputs. So see here, let's say this is my circuit, logic circuit. It has 8 inputs like I0, I1, I2, I3, I4, I5, I6 and I7. So these are my things: I0, I1, I2, I3, I4, I5, I6 and I7. Then finally what I can expect? I can expect output Y0, Y1 and Y2. Now tell me, what is my Y0? Y0 is I1, I3, I5, I7. So what it will do? It will take I1 like this, I1, okay, I1, I3, I5 and finally I7. It will perform the OR operation and it will give you the Y0. Okay, this will be my circuit. Okay, similarly it actually takes 3 OR gates like this. For Y1 also one more OR gate, for Y2 also one more OR gate. So for Y1, what is my output inputs for Y1? I2, I3, I6, I7. So I2, so I can take from here I2. So this is my I2. Okay, next I2, I3, I6, I7. I2, okay, I3. So this is my I3. I can take it from here. One more I3, I6. Okay, then finally I7. This is my I7. I can take it from here. Okay, similarly, what is Y2? Y2 is nothing else. I4, I5, I6, I7. So this is my I4. I can take it like this. I4, I5 will be this one, I6 will be this one, then finally I7 will be this one. Okay, so this is the logic circuit of my 8x3 encoder. Okay, so now I'll just conclude here. One more important thing here. What is that? The conclusion will be for all this whatever we have studied now. So mainly the decoder. In order to design a decoder, what it will do? It contains what in the decoder circuit, internal circuit. What it will be actually? Decoder contains all AND gates inside. Okay, we have seen yesterday, okay, which is also known as min-term generator, also known as address generator, anything. Okay, the demux, for demux we have seen yesterday what it contains actually. It also contains all AND gates only. Okay, we have seen what is demux. Demux is nothing else.
Sir,
Yes, tell me.
sir, one doubt.
Yeah,
Y2 is not like I2.
Y2 is I4, I5, I6, I7. What is I4? See
Uh,
here, I4, I have taken I4, I have taken I5 from here, I5, okay, and this is my I6, I have taken from here, I7, I am taken from here, here.
is it not like I2 into
No, it's
I1 bar, I2, I3 bar like that?
no. It's actually where how the truth table, from the truth table only. So see here I0, I'll be having for I0. You see here, this is actually 1. So here 1 means at that time what is which inputs are 1 here? Only here it is 1. So what is that? I1. So I have been taken I1. Similarly, next this is logic 1. So this logic 1 at that time what is my 1? I3. So I have taken I3. Okay. Next for this Logic 1, what is at that time input 1? The input will be I5. So I have taken I5. Okay. Next, at the end, which is I7. So like this, all the outputs will be Y0, Y1, Y2, all these things like this. Wherever 1 is present, what is the corresponding input at that time? 1. So you have to write down those logic expression in that way. Okay.
Is it not like min terms?
No.
Not
It's
that
it's
concept.
not type min terms. Okay. So this is the way it has inputs. From those inputs, it will be connected those particular inputs to get the final output circuit. Okay.
Okay, sir.
Okay, so this is the way a encoder can be designed. So finally, we have taken some of the clue points here. So decoder contains all the AND gates. We have already seen like how to design a decoder, half adder or half subtractor, full adder, and all. Whatever is there is actually takes all the inputs are actually all the inside the circuit is actually all AND gates. Okay. Similarly, in the DMUX, all the inside the circuit, all the things are AND gate. And finally, and encoder inside, what is that? Encoder contains all circuit will be OR gate. So we have seen it here. So it all has OR gates. Okay. Do you all understand or any doubt, students, on this? So this is the thing we have studied today. So this is actually combinational logic circuit. We have just end over the combinational logic circuit, and we'll start the like sequential logic circuit today. So we'll start now. So there is some problem. I'll just okay. So we'll start sequential logic circuit today. So mainly, I have already discussed little bit about what is combinational and what is sequential, students. So whatever we have studied till now is actually combinational logic designs, and today we are going to see like sequential logic design. Okay, this is one of the very important part of your gate point of view. Is also some of them are telling it's SLD kind of thing. Okay. And sequential logic circuits also somebody will take like SLC, anything. It's called sequential logic circuits also. Okay. So what is actually sequential logic circuit and combinational logic circuit? We have already seen combinational logic circuit, okay, which are actually CLC. We have seen how actually it's combinational logic circuit. Let's say this is my combinational logic circuit. So here whatever input I'll give, output depends on this particular input only. So here output is the function of this input. Okay. Output is the function of this input, present input. Okay. So present input. Okay. So this is my present input. But in combination logic circuit, sorry, in sequential logic circuit or SLD or whatever may be, the output is actually, it's actually a combination logic circuit. Along with that, there will be a feedback path. So the feedback path from here to this is my input, and this is the feedback path. Okay, this is the feedback path which actually stores the previous output. So what it will do over here, so here output is depends upon the present input, okay, as well as the past output. Okay, let's say here my present input is x1, I'll be getting output y1. Okay, now no, sorry, let's say previous input is x1, I'll be getting output y1. So this is my previous input. Okay, previous input, and this is my previous output. Okay, and now I'm giving input now x2. For this x2 I'll be getting output y2. Okay, so here y2 depends on what? It's a function of x2 as well as the past output y1. Okay, so so this is actually the particular thing in the sequential logic circuit. So what it will do, it will actually takes care about the past output also. It takes the past output also into the consideration to find out the present output. Okay, so in order to store this past output, what it will do, it will have some memory element over here. So here it is having memory element. So it's having memory element which stores actually the past output. Do you all understand, students? So this is final, this is your sequential logic circuit. It has CLC plus memory unit is called the sequential logic circuit. Okay, because output of this sequential logic circuit is dependent on not only the present input but also the past output. So this is my past output, okay, and this is my present input. Okay, so this actually passed output stored in the memory element. That's why we need a feedback path from output to the input. So wherever there is a feedback path from the output to the input, so these are all called sequential logic circuits. So like basic sequential logic circuits are like latches, flip-flops. Okay, next counters. We'll study all these things, students. Then shift registers. Okay, and Mille-Murray machines. So these are the things actually, Mille-Murray machines. So these are the particular things are the examples of your sequential logic circuit. Okay, so we'll start with basic memory element. Okay, so we need here what actually we have already studied about the combinational logic circuit. If we study the memory part, then we can able to study this sequential logic circuit properly. Okay, so we have already studied the combinational logic circuit part. I'm not discussing about this part. I'll just know that you all has known about it. Just I'll start with the basic memory element. Okay, so just see here, what is my basic memory element? So very important, students, please try to understand. I'm just slowly going because it's the first class about the sequential logic circuit. Okay, so memory element. So basic memory element is what? Let's say I'll draw one particular thing over here. Please try to let me know what is this actually, how it actually behaving. So this is my thing, and here I have done cross coupling. Okay, okay, so here my input is AB and here my output is Q and Q bar. Okay, so now tell me how this analysis will be, how will you analyze it? Okay, so see here, always remember, in case of sequential logic design, you would have first assume that initially there is outputs are present in this 0 and 1. Let's say you are assuming here initially that is a fundamental assumption. What is a fundamental assumption? The output of the memory element generally consist of 0 or 1 or something, some assumption. You may, somebody will take 1 0, somebody will take 0 1, like this. Okay, so and here in this sequential logic design, there are a memory element contains always two outputs. Okay, these two outputs are always complement to each other. Okay, if there is Q, this is Q bar. Okay, the output of the memory element generally represented with a variable Q. Okay, if it is Q, the opposite of is Q bar. So initially always remember it actually has certain assumption. So initially it has 0 and this is 1, let's say. Okay, so now you see here how to analyze it. So how can you tell that a binary digit is retained in this particular circuit? I'm slowly going toward the sequential logic circuit, students. Okay, so now tell me, here we have already assumed that my Q is 0 and Q bar is 1. So we have assumed here when Q is 0, let's say we have assumed here Q is 0. If Q is 0, what is that? If Q is 0, Q is connected now to where? Q is connected now to B. So if Q is 0, my B is also 0. Can I say like this? If B is 0, tell me what is Q bar? So this is what type of circuit, students? A NAND gate. I am just sorting a NAND gate like this. If I'll give 1, I'll get 0. If I'll 0, it will be 1. So obviously if B is equal to 0 now, so obviously I will get what at Q bar? Q bar will be 1. If Q bar is 1, then obviously Q bar is connected to where? A. If Q bar is 1, my A is 1. Okay, if A is 1, then obviously what is my output? It's just like an inverter, students. So it will give my output Q is 0. So finally what we have achieved? We have assumed that Q is 0, and after the final analysis I have retained the same value Q is 0. So what is happening here? The above logic circuit actually retains a binary digit. So what it will do? This circuit retains a binary digit. Am I correct? So it actually retains a binary digit. Okay. So now you tell me when Q bar is 0. Now sorry, Q bar is 1. So if I am taking Q bar is 1, obviously now A is connected to 1. So A is my 1. So if A is 1, my Q is 0. Q is 0. Okay, if Q is 0, Q is connected to B. So B is also mine 0. If B is 0, this is just a inverter. So B is 0 means I will getting Q bar is 1. So see here, I have been assumed 1 and finally I have retained also 1. So what actually this particular logic circuit, the above logic circuit retains A binary digit. Okay, it retains a binary digit. Okay, so this is the basic element in the memory unit. Okay, so see here, for n bit memory element in such circuits, there is n such circuits. So this actually retains what? Only one bit at a time. So let's say we want to retain, let's say 10 bits. So what I will do, I have to connect such a circuit like this. I will make it so 10 such circuits I have to design, so which retains actually 10 such bits. Am I correct? So this is the basic memory element, students. Okay, so now tell me one more important thing. So what we have done here, we have already studied about the CLC. Okay, now we have taken the feedback, and along with the feedback how it works, that actually sequential logic circuit. Very simple. So now tell me, it actually retains now 0 and 1, whatever we assume, that actually it retains. Now the thing is how it will store that binary value. Okay, so whatever my desired value, how it stores. Again there is this too. Okay, so now tell me how it will store. So in the previous circuit, what we have seen, it retains whatever we assume, that retains actually that particular circuit. But I want my desired value to be stored. Now I want 0, and let's say after 10 minutes I want 1, after 10 minutes I want again 0, after 10 minutes again I want 1. So my desired value is my requirement. According to my requirement, it's to store. Am I correct, students? So see here, for that what you need to do, you have to do certain modification. What modification you do? So see here, the modification to store a binary value. The binary value is what? My desired value. Am I correct, student? My desired binary value. So I want now to store actually 0. Let's say tomorrow I want 1. Let's say after some time I want 0 again. So how it will, some modification I will do to the particular circuit, then it will do that such particular bits to be stored. Okay, so see here what I am going to do here. What is the circuit diagram I will do? What is the circuit modification I will do? Initially I have actually circuit like this. So the circuit is like this. Okay, so this is the way. Okay, I'll do actually some modification and then I'll explain. So here I have done 4 NAND gates. Okay, 4 NAND gates like this, and here I have taken and connected here and connected here. So this is my Q bar, and this is my A, B. Okay, so what we have done here, I have extra connection I have done. So this one is connected again wrong. Okay, this is the circuit. Okay, so what I have done here, I have just cross coupled. I have taken from Q, connected to another input. So there are how many NAND gates now? The NAND gates are 1, 2, 3, 4. 4 NAND gates. Okay, initially there are 2 NAND gates. From these NAND gates, we have seen that how my value get retained. Okay, and we have analyzed it and we have seen here. Now in this case, what I'm going to do, whatever my desired value, let's say I'm going to like store now 0, and after some time I want to store 1. Okay, so for that what I have to do, just see here, initially every time you have some assumption. Actually, what is assumption? Let's say this is initially 0 and 1. Now before that you have to have some fundamental assumption. In order to analyze it, there will be some fundamental assumption you need to know. What is that fundamental assumption? The first assumption is a memory element contains 2 outputs. Okay, a memory element contains 2 outputs. So these are all fundamental assumptions. Next, these 2 outputs are complement to each other. 2 outputs are complement to each other. Complement to each other. Next, last one is the output of the memory element generally represented with a variable q. So variable q, obviously complement is q bar. Okay, these are my basic assumptions or fundamental assumptions. Then I will start analyzing this particular circuit, whether I am able to store my desired value or not. Okay, that is my fundamental requirement. Am I correct, students? So So see here, as we know that what is NAND gate, so these are all NAND gate. What is my functionality of the NAND gate? Before that, I want to tell you a little bit about the NAND gate. We have already studied much about the NAND gate. So see here, what is NAND gate? A, B, my output is nothing else, A and B bar. Okay. So 0, 0, 0, 1, 1, 0, 1, 1. So if it is 0, 0, I will be getting 1, 1, 1, 0. So this is my NAND gate functionality. So see here, what I will actually suggest here, when by looking into this, what we will get here, when one of the input, okay, when one of the input is 0, so what we can get here, output is always 1, output is 1. Am I correct? So one of the input is 0. In this case also, one input is, both the inputs are 0, I am getting output 1. In this case also, one of the input is 0, I am getting output 1. One of the 0, output is getting 1. When all the inputs are 1, what I will get? When all the inputs are 1, then my output is 0. Output is 0. Okay. Next, when one of the input is 1. Now tell me, when one of the input is 1. One of the input is 1. So what I'm expecting? Then output depends on other input. Am I correct? Then output depends upon other input. Am I correct, students? So if one of the input is 1, so see here, one of the input is 1, it depends on other input. So see here, if it is 1, it depends on this other input. Here 1, it depends on 0, whether it's 0 or 1, depending upon that, it's provide me output. Okay. So these are the fundamental thing of the NAND gate. While analyzing, we are going to consider these fundamental things of the NAND gate. You have already studied it actually, but I want to see what is happening actually with this. Okay. Now tell me, let's say my circuit is like this. Let's say I'm giving how now I'm analyzing whether it's like whether it's storing, the particular circuit is storing my desired value or not. That is my requirement. I have designed something. Now my thing is whether my particular circuit is storing my desired value or not. Okay. So just see here. So what is my circuit? My circuit is like this. It's 4 NAND gates. Okay, like this. 4 NAND gates. Here it will go to like this. Here it will go to like this. Okay, so this is my A, B, this is my Q, Q bar. Okay, I have assumed initially it is 0 and this is 1. Okay, so now tell me case 1. So case 1 is what? When A is 0 and B is also 0. Now tell me, now here A is 0, B is also 0. If A is 0, this circuit, what it will do, students? It will just, if it is 0, it will just invert it. It will give 1, it will also give 1. Now what I told to you, I have been assumed here, this is 1. If it is 1, 1 will go over here. So this is also 1. 1, 1, what I will get here? If it is 1, 1 in NAND gate, what I will get? 1, 1 means it's 0. So output, initially we have assumed 0. Now also I will getting 0. Okay. Now if it is 0, then obviously 0 will come over here. 0 and 1, what is that? 1. So what it will do actually? If my A, B 0, 0, what I am getting actually Q and Q bar. Okay. If it is 0, 0, what I am getting? I am getting 0 and 1. So 0 and 1 means I have already assumed I have 0 and 1 at the output. So I am getting whatever the previous value, the same value I am getting over here. Am I correct, students? Okay. If my input A be 0, 0, after analysis, what I am getting? I am getting whatever the previously, the next value, I am getting the same thing. So this is my initially we have assumed this. After analysis, taking a equal 0 and b equal 0, what I have achieved? I have got the same value again, 0 and 1. So what actually, if a be 0, 0, what it will do? It actually stores the previous value. It actually holds the previous value. You can take that it actually holds the previous value. Okay. So now tell me case number 2. So do you all understand, students? Very important, I'm telling. If you don't understand this, it's very tough next things to understand. Okay. So please try to understand the things. So if you did not understand, see this again. So this is my, again, this is the digital circuit. So what is my aim, students? My aim is whether this digital circuit stores my desired value or not. Sometime it should store 0, sometime it should store 1. Okay. Am I correct? So this is my logic circuit. Okay, so this is my A and B, and this is my Q and Q bar. Initially, I have assumed what? Initially, before the analysis I have assumed this 0, this is 1. Okay, now let's say my case 2 is A is 0 and B is 1. Okay, my A is 0 and B is 1. So now if A is 0, B equal to 1. So see here, if A equal 0, now my A is 0, B is 1. Okay, so if it is 0, what it will do? It will just invert. This circuit up to this is nothing else, it's just a inverter circuit. These are all inverter unit. So don't need to worry about it. Inverter unit. Okay, so if you put 0, it will give us 1. If you put 1, it will give us 0. Now the thing will start actually. Here Q is connected to my 1, 2, 3, and 4. Fourth NAND gate. Q is connected to my fourth NAND gate of one of the input. So 0 is there, so it will be 0. So 0, 0, what is that? 0, 0 means what is that? I'll be getting next value. What I'm getting at the next value? If it is 0, 0, I'm getting 1. Okay. So Q bar I'm getting 1. So because 0, 0, NAND gate is 1. Okay. Next thing is, if it is 1, now it will go over here 1. So 1, 1, what I will get? 0. So what we'll be getting here? So if A, B is 0, 1, I'm getting Q and Q bar is 0 and 1. What it tells? It actually reset my flip-flop. Okay, reset means it is storing 0. Okay, it is storing 0. Okay, it is storing my desired value 0. Okay, so now tell me case number 3. So my case number 3, again I am going to take A equal to 1 and B equal to 0. Okay, so at that time, so the circuit is similar, the same circuit I am analyzing, 4 NAND gates. Okay, third and fourth NAND gates are cross coupled each other. Okay, so this is my A, this is my B, and these are my 1, 2, 3, and 4. So this is Q bar. So initially I am getting here assumption here. My assumption is fundamental assumption. This is 0 and this is my 1. Okay. So if it is like this, what will happen? If I am taking A is 1, B is 0. So what I will get is just a inverter. 1, it will become inverted to 0. 0, it will be inverted to 1. Now tell me if this is my 0. So if it is connected to 0, what I will get? 1, 0. I'll get what? 1. So now 1 will be connected here. So 1, 0, again 1. Okay. So what will get here actually? Next state. Next state I am getting here. Okay. 1, 1. Okay. So what I am getting here actually? So 0, 1. Yes. Yes. So here I am getting Q. Q is actually 1. Okay. So here A, B, if it is A, B, 1 and 0, I'll be getting Q bar. What actually, if it is 1, 0, I'm getting actually set state. Okay, set state. Set state means it's actually 1, 0. Okay, so I'm getting here set state. Okay, and in the next case, case number 4, what we are getting here? So let's say I'm taking A is 1, B equal to 1. At that time, what I'm getting over here? So this is again my cross coupled. Okay, this is A, B. Okay, so I'm applying 1, 1. Here I'm assuming actually 0 and 1, Q and Q bar. So if it is 1, what I will get here? It is 0. This is also 0. Okay, then I'll be getting 1 here, 0, 1. I'll be getting 1, and here it is 1, 1, 0. I'll be getting also 1. So here initially I'll be getting 0, 1. Next state I'm getting 1, 1. 1, 1 means what actually, students? 1, 1 means can be neither Q and Q bar will be 1, 1. Tell me. No. If it is 0, it should be 1. If it is 1, it should be 0. So, but here I'm getting next state 1, 1. Next state 1, 1 means it's invalid. So if I'll give 1, 1 at the input, I'll be getting A, B, 1, 1 I'm giving. Then I'll getting Q and Q bar. If it is 1, 1, I'm getting invalid output. So invalid output, which is actually not valid. Okay, I'm getting 1, 1. Not every time Q and QR should not be equal. If it is 0, it should be 1. If it is 1, it should be 0. So obviously I'll be getting here wrong thing. Okay, do you all understand, students? So these are the 4 things we have achieved. So finally, what the truth table tells about me? The truth table tells about me here very simple. If it is A, B, this is my Q and Q bar. So 0, 0, I'll be getting the previous state here, previous state, Okay, for 0 1 I will be getting reset state. Reset state means q is 0, q bar is 1, which is called the reset state, or sometimes you may tell also reset state as off state, and also you can state 0 state, any name. Okay, so 1 0 I'll be getting 1 0, which is also called as set state or on state or 1 state. Okay, any name. Okay, next to 1 1, which is actually invalid. Invalid means sometime it is 1 1, sometime it is 0 0, like this will get, which is invalid. So it will be never possible. If two outputs are complement to each other, I should get, it should be actually 1 0 or 0 1. It will be never like 1 1 all. So that's why it's a invalid source. So this is the truth table. You can see what I am doing here. Actually, whatever the desired value, the previous value, it holds the circuit, holds the input, sorry, holds my output, and here I'll be desired value 0, it's storing 0, it's storing 1. My desired value is getting stored. Whenever I need, I'll give a 0, b equal to 1, I will store 0. Whenever I want to store 1 actually in my memory element, I'll give 1 and b is equal to 0. Okay, do you all understand? That's why it's just a basic memory element. Okay, so basic memory element, also it's called the latch. This is also called the latch. Okay, do you all understand? So it's very simple. Now we'll go to the next part. Any doubt on this, students? Very simple, whatever I have explained, nothing else. So next we'll go to the flip-flop. What is the difference between latch and a flip-flop? We have just discussed now latch. What is the difference between a latch and a flip-flop? Latch is nothing else. It actually, according to the input, up to it will control with the help of input. Up to when the input won't change, my output won't change. Okay, but in flip-flop there will be a controlling parameter. What is that controlling parameter? Clock is actually the controlling parameter. Okay, controlling parameter. So depending upon the clock pulses, it will change my requirement. It will be going to store 0 and 1 or what previous value, or it will be invalid depending upon my controlling parameter. I have to control here with the help of a clock signal. So what is the clock signal? All of you know that. What is clock signal? This is my clock signal. Okay, it's a pulse of square waves, nothing else. 0 1 0 1 0 1. Okay, if this is nothing else my t off, and this is nothing else my t on. So duty cycle is what? So this total time period is t on plus t off. What is duty cycle? Duty cycle is nothing else, t on divided by t on plus t off. Okay, what is duty cycle of clock? Duty cycle of clock is nothing else, t on divided by t on plus t off. Okay, which is nothing else, t on divided by t, capital D. Okay, and always duty cycle is expressed in the form of percentage, so it will be nothing else, t on divided by t multiply with 100. So this much of duty cycle percentage. Okay, any doubt on this, students? Very simple. Okay, so this is my controlling parameter. Depending upon this controlling parameter, we are going to store in my memory element, whether I have to store 0 or I have to store 1, depending upon this particular controlling unit, the clock pulse, we are going to store our requirement. So in the flip-flops, what you have to do, there are many types of flip-flops are there. Okay, so we'll start with in any flip-flops, what we are going to study. Actually, first we are going to study actually what is the logic symbol of that flip-flop. Okay, I'll tell you what are the different flip-flops, don't worry. Second one, we are going to study what is the logic design. Okay, next we are going to study truth table. Okay, next we are going to study the characteristic table. Okay, and next the characteristic equation, and then we are going to study the state diagram. Okay, and finally we are going to study the excitation table. Okay, so these are the things we are going to study for all the flip-flops. So there are many flip-flops are there. What are those flip-flops? SR flip-flop, which is also called as set reset flip-flop. Okay, so next there is JK flip-flop. Okay, JK flip-flop. There will be D flip-flop. Okay, D flip-flop is called the delay flip-flop. Okay, next there will be T flip-flop. T flip-flop is nothing else. It's called the toggle flip-flop. We'll see all these things. Don't worry, students. T flip-flop. So these are the basic flip-flops, and there will be another one, master slave JK flip-flop, MS JK flip-flop. Okay. So in order to avoid certain conditions, we have another flip-flop, special type of flip-flop, which is MS JK flip-flop. For all these 4-5 flip-flops, we are going to study what is the logic symbol of that particular flip-flop, logic design, truth table, characteristic equation, then state diagram, and finally the excitation table of it. Okay. So we're going to see all these things one by one of each flip-flop. So we'll start with our basic flip-flop. Okay. So what is the main difference between the latch and flip-flop? Do you all understand? So in latch, whenever input will change, then only my desired value, the requirement of the desired value going to store is going to change. But here, depending upon the control input is the clock. If my clock is telling at positive edge, I am going to store 0. If at negative edge, I am going to store 1. Depending upon the controlling parameter, my flip-flop will change my output. Okay. Do you all understand, students? Now we'll start with the basic flip-flop here, SR flip-flop. Okay. So what we are going to study, as I told you, SR flip-flop is a sequential logic circuit, which is also called as set reset flip-flop. Okay, set reset flip-flop, set reset FF, set reset flip-flop. So see here, first what I have told, the logic symbol, First we are going to start with logic symbol. Okay. So here, logic symbol is very simple. Flip-flop means it has SR, 2 inputs, and it has 2 outputs. Okay, 2 outputs. This is my SR, FF. So this is my S and R, and there will be extra thing will be the clock. Okay, because clock is the controlling parameter. With the help of clock, it is going to store the desired value. At up to what time it will store 0, up to what time it will store 1, up to what time it will hold. Okay, it depends upon this clock. Okay, so these are the 3 inputs, and finally my output will be Q and Q bar. As I told, the fundamental assumption, any memory element, it has 2 outputs. Okay, and both of them are complement to each other. Okay, do you all know about it very well? Okay, next, after logic symbol, I have told you what we are going to study. We are going to study the logic diagram. So logic diagram, whatever we have done till now, is actually the set reset logic diagram design, but here extra thing is actually the clock pulse. Okay, so here we see what is the logic diagram. Basic logic diagram is like this. So we have seen already this one. It has 4 NAND gates. Okay, so this is my SR latch. Actually, what is this? This is my SR latch. Okay, if I want to convert this SR latch to SR flip-flop, what I have to do? I have to just apply a control input, which is actually clock pulse. Okay, so this will be now converted from my SR latch to SR flip-flop. Okay, do you all understand, students? So here, how many NAND gates? So 1, 2, 3, and 4. So now the thing is, how my truth table will be get obtained from this. So next thing is my truth table of this particular SR flip-flop. What is truth table? Was the relationship between input and output. Obviously the same thing. So here the clock is actually taking the major criteria. So my clock is initially, let's say 0. If clock is 0, whatever my S and R value, it will hold always the previous state. Okay, so this is my Q and Q bar. It will always hold the previous state, previous value. You can say previous value. Okay, previous value. Do you all understand, friend? It will not going to change. It will just hold the previous value. My clock is 0. It will not. It will just act like as it is. It retains that particular value. It will not change it actually. Whatever my desired value, it will not get it. Okay. Now, if my clock is 1, now I am applying the clock here. If clock is 1, okay. So I will tell you what is clock is 1 and all later on, while we are using the clock for the triggering pulses. I will tell you at that time. So my S and R will be 0, 0. So we have already studied, if S and R 0, 0, what I will get the output? It holds the previous value only. Am I correct, students? We have already told, we have analyzed this circuit already. Okay, it will give me previous value only. Now tell me, now again clock is 1. If it S is 0, R is 1. So what it will do? It will reset that. If R is 1, it will reset my output. Reset my output means whatever will be there, it will change my output to 0. Okay. So if it is 0, it is 1. So this is called reset state. reset state. So whatever here previous value, let's say it is 1 0 or 1 1, whatever may be, if you give s equal to 0, r equal to 1 with clock equal to 1, it will just made this output to 0, nothing else. If made the output 0 means obviously my complement of the output is 1. Am I correct, students? Okay. So now this is my clock 1 again. So this is 1 0. So what it will do, it will set whatever my previous value, it will just set means it will provide my output equal to 1, and this is called my set state. This is my set state. Okay. Now again clock is 1, s is 1, r equal to 1. At that time it is invalid state. Invalid state. So why is it? Because it's getting actually always 1 1, same output for the complements also, it's getting the same out. So this is my truth table of my SR flip flop. Okay, do you all understand, students? So here only the difference is the clock. We are controlling our the flip flop to store the values depending upon this clock pulse. If you give clock pulse 0, if you are not giving the clock pulse, whatever my S and R value, it holds the previous state, because this is just a flip flop. Flip flop means it depends upon the controlling parameter clock pulse. Okay. Now we'll go for the next part. What we are going to study in the next part, fourth one, which is actually the characteristic table. So what is the characteristic table? The characteristic table tells about how the character of the flip-flop, the state of the, so there will be two states actually of the flip-flop. What are those states? One is Qn, another one is Qn plus 1. So we are assuming initially some state, initially. So Q1 is nothing else, the flip-flop before applying the clock pulse or signal, okay, which is actually the state of the flip-flop. Q1 is nothing. There are two states always. A flip-flop has two states. That's why a flip-flop is also called the two stable states, or it's called the stable multivibrator, okay, because it has two stable states. Okay, what are those states? A Qn and Qn plus 1, 0 and 1, two states only always. So the state of the flip-flop, what is Qn? The state of the flip-flop before applying clock pulse, before applying clock pulse, applying clock pulse is called, clock pulse is called present state, is called present state. Okay, is called present state or Qn. Understand, students? Now the state of the flip-flop after applying the clock pulse, after applying clock pulse, applying clock pulse. Now I have applied the clock pulse. Depending upon, now what it will do, after applying the clock pulse, depending upon the inputs, it will change my output, it will store the desired value. Okay, after applying the clock pulse is called next state. Next state is defined as Qn plus 1. Qn is present state, n plus 1 means it's a next state. You all understand? So what actually characteristic table will tell? Characteristic table will tell the relationship between present state and the next state. Okay, depending upon, it will swings from the present state to the next state. At that time, what is my corresponding inputs of S and R? Okay, so see here, what a characteristic table, it tells about Qn, S and R. Okay, Qn, S and R. What is my next state? Qn plus 1. Let's say Qn is 0 now. Okay, Qn is 0 now. If S and R is 0, what it will do for S? What is the SR truth table? Actually, SR, if it is clock, okay. So if it is 0 0, what it will do? If the clock is 1, what it will do? It will hold the previous value. Am I correct, students? So what is the previous value? Previous value is nothing else, my this one. Previous value, presently it has 0. What will be my next state? Next state also the previous value, so it will actually 0. Do you all understand, students? Now if it is 0 and this is 0 1, 0 1 means what it will do? If it's 0 1 means it will reset whatever may be my previous value. It will be not, it will not be going to consider, it will just reset my flip-flop. Reset my flip-flop is 0. In the next state it will just reset. Now 0 1 0, if it is 0, previous value is 0. Now if I will apply 1 0 at that time, what it will do? It will not see whatever my previous value, it will just set at the next output. Okay, next value, next 0 1 1. If it will be 1 1, what will it will do? Whatever my previous value, it will be not consider. If it is 1 1, it should be invalid. As we know that for my 1 0 1, it is Q is 0. Okay, for 1 0, Q is 1. If it is 1 1, Q is don't care. Okay, invalid. Okay, that's why we got here don't care. Okay, do you all understand now? So now Qn is 1. So now Qn is 1, S and R 0 0. What it will do? Whatever my previous value, the same value it holds. So output is 1. Next state is also Qn plus 1 is 1. Okay. So now next Qn1. So this is 0 1. What it will do? It will just check reset is 1. So obviously it will make my next state will be 0. Whatever my previous state, it will be don't care about it. Okay. Next Qn is 1. Next 1 0. What it will do? It will just set my output to 1. Let my flip flop to 1. Okay. Next 1. This is 1 1. 1 1 means invalid. Whatever my previous state, it will not consider. In the next state, I will getting always the invalid output. Don't care. Okay. Do you all understand, sir? Or any doubt on this? Please let me know. Any doubt on this? Okay. So this is the thing. Now this is the characteristic table. What characteristic table tells? It tells about how the relationship between the present state and the next state. So these are my present state. Okay. If I apply this S and R value, how the next state will I get? Okay. So what it will do mainly, it actually takes what is the XR S and R. SR 0 0 means it holds. It holds means whatever the present state, in the next state also it holds. Okay. 0 1, it don't care about the present state. What is it? In the next state, it will just make the reset, because my reset is 1. So set, it will be set the flip flop to 1. Now 1 1 means whatever my present state will be, it will not take, it will just make it to don't care. Do you all understand, student, or any doubt on this? Please let me know immediately. Okay, like this was my characteristic table. It actually characterize my flip flop. It will be characterized between the present state and the next state. Okay, and the next thing, so characteristic equation. So this is my fifth point of any flip flop. There will be this. These are the points you need to describe. So what is characteristic equation? If you solve the characteristic table, I'll be getting characteristic equation, obviously. Okay, what the characteristic of an flip flop? So what is characteristic equation? It actually gives the relationship between present state and the next state. Okay, so it tells about what will be my next state equation. So characteristic equation is nothing else, what should be my next state equation in terms of present state. In present state is nothing else, Qn. How Qn plus 1 depends to Qn with the inputs present of input S and R. So for that, what you need to do, you need to solve the characteristic table. How to solve the characteristic table? This is nothing else, my three variable K-map. So this is Qn, S and R, three variables which actually varies, then my characteristic next state will get varied. Okay, so for this, what I have to get, if I want to find out Qn plus 1, I will be having three variables to solve it, Qn, S and R. So here it is Qn, S and R. These are the three inputs. So obviously there are 8 possible combinations of cells. So this is my Qn, Qn bar, sorry, Qn bar and Qn. So this is my Qn bar and Qn, and this one is S bar, R bar, S bar, R, SR and SR bar. And we know that minterm positions, these are 0, 1, 2, 3, 4, 5, 6 and 7. Now if I can put from this characteristic equation, what is minterm 0? This is my M0, M1, M2, M3, M4, M5, M6, M7. Okay, where I am getting 1 at M2, M4, M2, M4, and one where it is else, M6, at M6. Okay, and where I'm getting don't care, students, I'm getting don't care at M3 and M7. Okay, M3 and M7. This is my don't cares. Okay, do you all understand? So now, in order to solve for Qn plus 1, so what are the different what are the groupings will be possible? We have to first check octets. There is no octets, so obviously we'll go for quads. Okay, what are the quads present? Yes, there will be a one quad. With the don't care, I can take it. So if I take this, next there is no quad, I can pay it up because these two are adjacent minterms. So what will be my final? Here the common is actually here the common is nothing else, S, and here what is my common here? Qn and R bar. Okay, so finally I have got Qn plus 1, S or Qn R bar. So this is my characteristic equation. Okay, this is the characteristic of my flip flop. Okay, any doubt on this, students? So if there is no doubt, we'll go for next. Actually, what is the next? Next thing is sixth one, which is actually state diagram. What is state diagram? State diagram is nothing else. I have discussed with you till now. What is state actually? There are two states of the flip-flop. What is those states? Either there will be a present state, or there will be a next state. So these are the two states. Okay. So present state is nothing else my q1, and next state is nothing else my q1 plus 1. Okay. So what it actually tells state diagram? State diagram is nothing else the representation of state transition. State transition means how the state transits from present state to next state, how it transits. Okay, means qn to qn plus 1 with respect to external inputs. Okay, do you all understand, student? State diagram is nothing else the representation of the state transition. Okay, changing from present state to the next state in presence of external inputs. Okay, how it changing? What are the states actually, students? States are actually nothing else 0 and 1. So let's say initially it is present state is 0, next state is 1, let's say. Okay, so at that time how my inputs are behaving? If a present state is 0 to 1, it is going from 0 to 1 like this. Transition state diagram is nothing else is the representation of state transition from present state to the next state in presence of the external inputs. Okay, what are the external inputs I have? S and R my external input. So while transit from the 0 to 1, so what are my S and R? Where I will get from here? So see here, transit from 0 to 1. So I am transiting from 0 to 1. So my present state is 0. Where? Here. Here I am transiting from 0 to 1. What is at that time SR? SR is 1 0. Am I correct, students? SR is nothing else my 1 0. Okay. Now let's say I'm transit from 1 to any other case 0 to 1 is possible? No. Now tell me 1 to 0. I'm transit from 1 to 0. At that time, what is my SR? 0 1. So if I am transit from 1 to 0, then at that time what is my SR? My SR is 0 1. Okay. Now if I am transit from 0 to 0, so let's say I'm transit from 0 to 0. What is my SR? SR is 0 0. Also, if I'm transit here also I'm transit. Okay, here also I'm transiting from 0 to 0. So at that time what I'm getting here? SR will be 0 0 and 0 1. So if I'm transiting from 0 to 0, so if I'm transiting from 0 to 0, what is my S and R value? It is 0 0 and 0 1. So 0 0 0 1, can I write down like 0 and don't care? S will be 0 and R will be either 0 and 1. So I can write down 0 and don't care. So SR will be 0 and don't care. Am I correct? If it is transiting from 0 to 0, means next state is 0, previous state is all, sorry, present state is 0 and next state is also 0. So at that time, what is my S and R? S and R is 0 and don't care. So similarly, if I am transiting from 1 to 1, so at that time, what is my SR, students? If I am transiting from 1 to 1, so see here, I am transiting here from 1 to 1. If I am transiting here from 1 to 1, so this is one case. Again I am transiting from 1 to 1. So at that time what is my SR? 0 0 and 1 0. So my SR will be 0 0 and 1 0. So if I can write down, this will be don't care 0. Okay, do you all understand? So what is my state diagram? My state diagram is the representation of the state transition from present state to the next state with the presence of the external input. So during 0 1 my SR is 1 0. Okay, during 1 to 0 state transition my SR is 0 1. During 0 to 0 transition my SR is 0 don't care. During 1 to 1 transition my SR value is don't care 0. Do you all understand? This is my state diagram of SR flip flop. How my state transition is happening between present state to next state. Okay, always there will be two states of the flip flop. The two states are nothing else my 0 and 1. Okay, so next thing is the last part of it is excitation table. Excitation table, which is actually seventh one of any flip flop. You have to do all these things, students. What is excitation table? Excitation table will tell about, shows the different possible state transition in presence of the flip-flop input. So it is nothing else, it's just a tabular form of this state transition, nothing else. Okay, excitation table mainly shows, what is excitation table? Excitation table shows the different possible state transitions, state transitions in presence of the flip-flop inputs. In presence of the flip-flop inputs. Okay, in presence of the flip-flop inputs, how the state transition happening? So state transition is from where actually? Qn to Qn plus 1 always. Okay, at that time what will be my S and R? So here inputs will be Qn plus 1, outputs will be my S and R. So state transition from 0 to 0. What is my S and R at that time? So 0 to 0. What is my S and R at that time? 0, don't care. Very simple. State transition from 0, 0, 0 means present state is 0. Next state is also 0. Okay. So do you all understand? If present state is 0, next state is also 0. At that time, what is my S and R? S and R is nothing else, 0 and don't care. Okay. Now this 0 1, at that time what is my S and R value? If it is 0 1, 0 to 1, state transition from 0 to 1, at that time what is my SR value? SR value is 1 0. Okay, similarly state transition from 1 to 0, 1 to 0 means this one. If state transition from 1 to 0, what is my SR value? SR value is 0 1. Okay, if state transition is 1 1, what is my SR value? SR value is, if 1 to 1 like this, what is my SR value? Don't care, 0. So this is nothing else my excitation table, students. Very simple. What excitation table tells? Excitation table shows the different possible state transitions. Different possible state transitions means state transition 0 to 0 or 0 to 1 or 1 to 0 or 1 to 1. At that time, what are the flip-flop inputs? That actually told my state excitation table. Okay. So this is the excitation table of the SR flip-flop. Okay. Any doubt on this, students? For today, this much only. Any doubt on this? Please let me know immediately.